Image method or method of images is actually method of image charges. What is this method of image charges? It is a technique by which one can determine potential or field intensity. Its specialty is it works where other regular or traditional methods of calculating potential and intensity fail. It is used and useful to have a solution for problems involving conductors or conducting bodies in addition to charges and currents. The basis of this technique, method of image charges, it lies on two laws. One is Poisson's equation, another is uniqueness theorem. What is Poisson's equation? Del square V is equal to minus rho by epsilon. Here V is electric scalar potential and rho is volume charge density. We can notice it is a differential equation, partial differential equation. It can be solved to find potential or potential function. During the solution process, first we get general solution. When boundary conditions pertaining to the given configuration, they are applied to the general solution, specific solution or particular solution, it comes into being. This is the actual solution that is required. It is this solution that is actually pertains to the given source configuration. Now, let us suppose there are two different configurations. They are different, but let us suppose their boundary conditions are same. Configurations are different, but there is a match between the boundary conditions. Because of the match between the boundary conditions, Poisson's equation gives same specific solution in both the cases, same potential function. Even though configurations are different, solutions of Poisson's equation, they come out to be the same. This is an important observation. In fact, this is the basis for the technique behind the method of image charges. In practice, in the real world, the sources, charges and currents, they are mounted near to the ground or earth. Earth is a conductor. If the sources are far away from conducting objects, one can use regular methods to find potential and field without much difficulty. Presence of conducting objects, it alters the potential distribution, field distribution, and we have to take their presence into account while calculating potential or field. Regular methods that use Coulomb's law, Gauss law, or Biot-Savart law, Ampere's law, they don't take the presence of conducting objects into account while calculating fields or potentials. So they are not of much use. To overcome this difficulty, image method has been developed. To understand this method, consider a problem which involves charges and or currents along with conducting bodies. In the process of application of image method, to find a solution to this configuration, as a first step, another configuration is imagined, considered. Let us call this configuration as equivalent configuration. Equivalent configuration is different from the original configuration. Usually in the equivalent configuration, the conducting bodies or conductors, they are replaced by charges and or currents. These charges and currents are called image charges, image currents. The selection or guess of the equivalent configuration is not arbitrary. Selection should be such that The equivalent configuration is amenable for solution. Solution for this configuration must be available, or we must be able to find a solution with regular methods. In addition to this, the equivalent configuration must have boundary conditions that match with the boundary conditions of the original configuration. These two aspects are to be ensured while selecting the equivalent configuration. As equivalent configuration has solutions available or capable of giving solutions through regular methods, one can say that it is a configuration with solution existing or available. Now, we have noticed while discussing about Poisson's equation, when boundary conditions are same, the solutions are also going to be the same. Now, one can easily understand when one say the solution of the equivalent problem is the solution of the original problem. Another aspect which is basis of method of image charges is uniqueness theorem. This theorem ensures uniqueness or distinctiveness of the solution given by method of images. In other words, uniqueness theorem guarantees that the solution obtained through method of images is the only solution and no other solution exists for the problem on hand. With this small introduction to method of images, now we move into the actual session where basic and interesting points and also the points that can take you even to higher levels in understanding image method are discussed and described. Electrostatics image method series on electromagnetic field theory, lecture number 1.55. Before going deep into the topic, let us consider a few basics which are essential to go deep into the subject. Image method is also known as method of images. It is essentially a comparative method. It involves comparison between two configurations. It is one of the solution procedures for Poisson's equation. It is helpful in the determination of electric and magnetic fields and potentials too when there are reflecting boundaries and a high degree of mirror reflection symmetry. So this method is most suitable when the configuration involves reflecting boundaries and high degree of mirror reflection symmetry. It does not require the governing partial differential equation to be solved. It is a plus point. The labor, the difficult involved in solving differential equations, Poisson's equation is a differential equation. That difficulty that is there in its solution, that is not there. It does not require the governing partial differential equation to be solved. Notice Poisson's equation is a differential equation. Solution of Poisson's equation, that process, not only Poisson's equation, any differential equation, its solution process involves a lot of labor, lot of hard work, lot of difficulty. In this technique, it doesn't require the differential equation to be solved. Therefore, we are saved from that arduous job. The solution is obtained by superposition of identified solutions, each of which satisfies Poisson's equation. This method was due to Lord Kelvin. He was born as William Thomson, lived between 1824 and 1907. He was an Irish mathematical physicist and engineer. Originally, his attention was mainly towards electrostatic problems. Later, Maxwell extended his technique to spheres and sphere plane combinations. Apart from Kelvin Maxwell, Harold Hague genes are major contributors for the development of this particular technique. The basic requirement of this method is the conditions at the boundaries shall be correctly represented by the images. Actually, this method involves guessing some configuration involving certain imaginary charges. These charges are called images. Some more information pertaining to images will be given in due course of time in the present session itself. The solution procedure involves guessing another arrangement which is amenable for solution. Of course, this arrangement involves some image charges and currents. This arrangement, which is a guesswork, its boundary conditions must be same as the original configuration. So guessing another arrangement, this arrangement must be amenable for solution, and this arrangement must give boundary conditions same as the original configuration. So 3 steps are there. These are the basic steps. These are critical steps that are there in the method of images. As boundary conditions match, the solution of the equivalent configuration naturally satisfies the original one. When boundary conditions are same for 2 configurations, the solution of one becomes valid for the second 2. The distinctiveness of the solution is guaranteed by uniqueness theorem, which says there is only one possible solution that meets the requirements in terms of boundary conditions. The uniqueness of the solution, it is guaranteed by uniqueness theorem. Here, general principles pertaining to image charges, they are enumerated or given. The magnitude of image is same as the source, but polarity is opposite. The image and the source are at the same distance from the constant potential plane. The geometry is reflected in the constant potential plane as in mirror. Multiple sources produce multiple images like reflection from a mirror. Single or multiple sources and point or distributed charges in front of multiple mirrors also produce multiple images. When sources are several, images are also going to be several. When reflecting surfaces are several, images are also going to be several. Here is shown sources, source charges and their corresponding image charges and currents too. First 3 are charges, remaining 2 are currents. Now first one, plus Q, a point charge. It is there at a height of h from a perfectly conducting plane. Its image charge will be at a depth of h, which is the height of source from conducting plane. The image charge magnitude is Q, same as original source charge, but polarity wise it is opposite. Now another one is considered. This one is like a dipole, electric dipole, plus Q minus Q, and its image consists of another dipole. Its location is below the conducting plane at a depth which is equal to height of the source dipole from the conducting plane. So depth of image is equal to height of the source. But notice here plus Q in the image configuration is image of the minus Q in the original. Minus Q in the image configuration is image of the plus Q in the original. We go to third, charge distribution. Here also it can be considered as a dipole, but this dipole is in a horizontal plane. Its image, as usual, is at a depth which is equal to height of the original source charge distribution. Note plus Q in the image corresponds to minus Q in the original. Minus Q in the image corresponds to plus Q in the original. We consider 2 current loops. In the first configuration, the loop is in a vertical plane. Current is in clockwise direction. In the image also current is in the same direction. Of course, depth is equal to height. Depth of image is same as height of the original current source. Another current loop which is in a horizontal plane is shown as the last one. In the original, the current is clockwise, but in the image, the current is in anti-clockwise. These 5 distributions, source distributions, they are able to give some kind of familiarity, some kind of insight into the location and polarity and magnitude of the images. Fundamental steps that are involved in image method, they are given here. These methods are specific to planar geometry situations, but they can also be extended to non-planar ones in a prudent manner. What are the steps? Establish a constant potential surface, which normally is the exterior of a conductor. The potential of this surface need not be zero. Situate the image charge distribution, which is equal to source charge but opposite in polarity, at an equal distance on the other side of the constant potential surface. Now the conductor can be detached since its presence and impact is simulated by image charge distribution. When the number of charges, they are few, compute electric field intensity, and if number is large, potential at a general point in space. Work out other quantities like force, energy, etc. if necessary from the basic formulas of field intensity and potential which are available. These 5 steps, they give a lot of information pertaining to application of image method to solve problems that involve reflection symmetry. Now, to go a little more deep and to illustrate the applications of various principles that are discussed till now, various points that are described until now, we consider 3 configurations. These are configurations which involve point charge over a conducting plane, point charge near a grounded conducting sphere, line charge in parallel with a conducting cylinder. Before going to the actual problems, let me remind you basic point as far as this technique concerned is it involves guessing another arrangement. We have to guess, and it must be amenable for a solution. So guessing is there. It must be not arbitrary. It must be amenable for a solution. Usually it involves some image charges, currents, and also its boundary conditions must match with the boundary conditions of the original. These 3 aspects or 2 aspects must be there always in the mind. Now first configuration, point charge over a conducting plane. Here is a point charge Q. It is lying over a conducting plane. It is grounded. Therefore, V equal to 0. So to deal with without difficulty, we place the conducting plane over XY plane and adjust in such a way that the charge is over Z axis. Notice Q point charge is at a distance of D from the conducting plane. So this is the problem. Let us suppose we are interested to find voltage or field intensity at a point P which is located above this conducting plane, above XY plane. Ordinary methods, traditional methods, they are not of much use in the present case. Now let me state the problem. A point charge Q is located at a distance D above an infinite. This is infinite in extent, infinite in x direction, infinite in y direction. Grounded. Grounded means potential is 0, conducting plane. It is required to find the potential field at an arbitrary point in the region above the plane. We are not interested below. Our interest is above. Now boundary conditions. Potential V is 0 over the conducting grounded plane. Also V is 0 far away from the charge. These are the boundary conditions. Now, solution process involves imagination of another configuration whose boundary conditions are also same as these boundary conditions. That is, potential V is 0 over the conducting plane and V is also 0 far away from the charge. That second configuration is shown here. That equivalent configuration is shown here in B. First of all, we have to remove this conducting plane, remove, and replace it with the image charge minus Q at a depth of D from XY plane. As the configuration shown in B has boundary conditions which are same as the boundary conditions of the original problem, the configuration in B can be considered the configuration that is required for us and the configuration that is capable of giving valid solutions for the original problem. Let us move further. Another configuration, it results when conducting plane in the original is replaced by a point charge minus q called image charge exactly below original charge q at a depth of 2d. This arrangement can be found equivalent to the first one because both satisfy the same boundary conditions. One can compute potential over xy plane, any point over xy plane, it can be found 0. One can also calculate potential at a faraway point. There also one can find potential 0. So therefore, the configuration that is given in B is equivalent to the original one. That's what he's telling. Potential, field and force due to this, they are same. Energy, however, is exactly half of that in the equivalent problem. Reason is field intensity is non-zero above the plane, but it is 0 below the plane in original problem. But in the equivalent problem, notice field intensity is non-zero both above and below the conducting plane, above and below the xy plane. When field intensity is non-zero, energy is non-zero. Therefore, in the equivalent problem, energy exists above, energy exists below. In the original problem, energy exists only above xy plane. So in the original problem, energy is 1/2 of the energy that is there in the equivalent problem. Here are shown expressions for voltage, force, and energy. We consider another configuration, point charge conducting sphere. Problem is this, a point charge q is located at a distance of d from the center of a grounded conducting sphere of radius r. It is required to know the potential outside the sphere. Inside the sphere or over the surface of the sphere, there is no need to do any calculation to know the potential. Reason is it is a conductor, perfect conductor, and it is grounded. Therefore, potential is 0 everywhere over the surface as well as inside. Potential doesn't require any calculations to be done. Outside the sphere, we want potential. Of course, once potential is known, we can calculate field intensity and other quantities too. Boundary conditions. The potential over the grounded sphere is 0. Conductors are equipotential surfaces. Inside two, potential remains the same. Everywhere potential is 0. As in the present case, it is grounded. Now, traditional methods, they are of no use here to find potential. So, we go for method of images. In A is shown original configuration. In B is shown equivalent configuration. In the equivalent configuration, the original configuration sphere is replaced by a point charge Qi, and it is located at a distance of di from the center of the sphere over a line connecting source charge q with the center of the sphere O. Therefore, equivalent configuration consists of 2 point charges. One is q, another is qi. Qi is at a distance of di from center of the sphere. Notice r is the radius of the sphere qi. Now, with the help of trigonometry, it is possible to show that the original configuration and the equivalent configuration both give same boundary conditions. That is, potential over the grounded sphere 0. Another configuration, sphere is replaced by another point qi located at a distance of di from the sphere center towards the charge q. Potential or field due to this could be same. The same when we select the values of qi and di appropriately. Qi should be, it is not arbitrary. You have to select Qi equal to minus R by D capital Q. So if original source is positive, image source is negative. If original source is negative, image source becomes positive. Di, distance of the image charge from the center of the sphere. This distance also you should not select in an arbitrary manner. It should be r square by d. R, d, qi, everything they are depicted in the diagram. When these conditions are satisfied, the equivalent configuration gives boundary conditions same as boundary conditions satisfied by the obeyed by the original configuration. The force of attraction that exists between point charge and sphere, it can be calculated. Once we found that configuration in B is equivalent to configuration in A, we can use configuration in B to find potential, to find field intensity, to find force, etc. But we have to move with some caution. B is equivalent problem. Image configuration is equivalent to original. It is not equal. So certain alertness, certain caution must always be exercised in using the image configuration while obtaining solutions to the original problem. Third one, line charge and a parallel conducting cylinder is there. Both are running parallel. Let us first describe the problem. A straight line charge with a density lambda L in parallel with a conducting cylinder radius R. These two are there. Both are considered to be very long and distance between their axes is D. This is the distance. R is radius of the cylinder. Boundary conditions. The surface of the cylinder is an equipotential one. This is conducting cylinder, therefore it is an equipotential surface. Of course, if it is grounded, potential becomes zero. Let us suppose our requirement is to find field intensity at a point P somewhere here. We may be requiring potential or we may be requiring field intensity. Traditional methods, they are of no use. But if somehow we are able to convert this problem into a configuration that is amenable, that is acceptable to traditional methods of potential or field calculations, then our problem is solved. Of course, that is image method. Now, in B is shown another configuration. This configuration involves two line charges. One is, of course, original line charge lambda L. The second one, another line charge. It is used to replace the conducting cylinder. Here it is indicated by minus lambda L. Magnitude wise it is the same as the original line charge, but polarity wise it is opposite. It is placed at a distance of di from the center of the conducting cylinder over a line connecting original source line charge with the center. Now the distance di, it is not arbitrary. So he is talking about another setup derived from the original one by replacing the cylinder by an image line charge, let us say minus lambda L, located at a distance di equal to r square by d from the axis of the cylinder. Then this another setup becomes equivalent to original setup because both satisfy the same boundary condition. Potential or field due to this could be same when di is equal to r square by d. To get this condition, one need to have certain background in trigonometric relations. Now, note that in all the configurations, the polarity and amount of image charge is a guesswork, and selection of its location is by computation to give identical boundary condition. These are some of the points that are required to be given to you so that you can have at least a reasonably good level of understanding in image method. Hope you have a fruitful and enriching learning experience. Enough for now. See you soon.